Welcome. I want to show you how to do projectiles at angles. So we're going to go over the equations that you're going to use. Now the equations for projectiles at angles can be used for horizontal projectiles, which you already know. There's only a very slight difference in how you get the initial vectors for the vertical and the horizontal velocities for your projectiles. So let's start off by taking a look at a horizontal projectile. I can find a marker that works. Here we go. If I have a horizontal projectile and I fire it off of a cliff, it describes a parabola like this. And it has an initial Vx in the x direction, but Vy doesn't begin until after it starts to fall. So Vy initially is 0, and so there's no Vy to speak of. But if we are looking at a projectile that is fired from the ground to another place, let's say the projectile is fired in the upward direction like this, then the projectile describes a parabola like this. And we can look at the original vectors for Vx and Vy. We start with V naught, which is the initial velocity of the projectile. And we need to split this into an X and a Y component. Well, this describes a triangle here, a right triangle, and Vy, that's the portion that's going up when we fire it. And Vy is equal to the sine of the angle times the initial velocity. So I'm going to put the initial velocity in the front here. So we have V naught times the sine of the velocity. So let's go on and put that up here. So velocity in the y direction, and I'm going to put a comma here, and I'm going to say naught, V naught, because it's the initial velocity in y, because it obviously changes. V naught in the y is equal to V naught times the sine of the angle. Okay. Now in the x direction, we have Vx, which we could say that's Vx naught, but really it's just Vx because the horizontal velocity remains unchanged throughout the flight of the projectile. So I'll just call it Vx. It's going to equal to V naught times the cosine of the angle. Okay, so whatever this angle is. So let's label this Vx, and it's equal to V naught times the cosine of the angle. Once we have the initial x and y information, we can now solve this the same way that we would solve a horizontal projectile, or the way we would solve a free fall problem, or a combination of the two. So let's look at the equations that we need. So for dx, the distance that it goes in the x direction, normally that would be described by the velocity times time. So for a horizontal projectile, it's the velocity times time. But the velocity here is equal to V naught cosine theta times time. I'll put the time in a different color here. All right. So this first part right here is just Vx. So that's fairly straightforward. For the other one, for the y distance, dy, and I'm going to call this dy at some time t, because really the distance that it goes up and down varies depending on time. Dy at some time t is going to be equal to the initial velocity, which is v naught times the sine of theta. So that's the initial velocity times time, plus then we have the normal free fall 1/2 gt squared. So 1/2 gt squared, and g is gravity, which is 9.8 meters per second squared, or we can just use 10 meters per second squared. Notice that this is negative, so we could do v naught sine theta times t minus 1/2 gt squared, and then just use a positive value for g. It really doesn't matter, just as long as you remember that g is negative. So this entire term right here, after the first term from here over, is negative. It's subtracting from the initial velocity. If I throw something up, gravity subtracts from its initial velocity up until it begins to come back down again. So from these two things, which are really easily used for a horizontal projectile as well, we can go on and derive all the other equations that we're going to need. So the first thing I'm going to do is I'm going to look at the velocity at some time t. So I'll say the velocity in the y direction at any time t is going to be equal to the initial velocity, put the equal sign in there, times the sine of theta. Okay, so remember that this right here is just Vy. That's the same thing that we would use for free fall if I threw something up and then it fell down, except that I'm looking at V naught sine theta to get that. So it's equal to that plus GT, gravity times time. And remember, this gravity is negative, so we can go minus GT and just use a positive for gravity. But this term here is negative. So once we've got this, we can now solve for a special case. And that is, what is the time right here at the top? I'll call that T1. So when I fire a projectile up, at some point, its upward velocity, the y component, vertical velocity, becomes 0. And I can solve for that time fairly straightforward by just setting this equal to 0, right? So I have an initial velocity and some time, and at some point in time, it turns around and comes back the other way. So I can solve for that by just rearranging. And I'll say time at whatever time that is going to be equal to, and I'll call this, this is our V naught sine theta divided by G. And in this case, G is positive, because what I've done is I've moved this over to the other side. I've subtracted it from both sides. The minus signs cancel. So we end up with a positive value for time. Move it to the other side and then divide by G. So it ends up being positive. So V naught sine theta divided by 9.8, or V naught sine theta divided by 10. All right, so that's the time up to the top of the arc. Now I can also get the total time in the air under one specific condition. And that specific condition is that my target is at the same elevation as where I fired the projectile. So if I'm shooting from the ground to the ground, I'm not shooting up a hill or down over a cliff. If I'm shooting from the ground up and it's going to hit the ground at the same elevation, then I know that the time in the air is just twice the amount of time that it takes to get to the top of the arc. So it goes up, that takes half the time, and then it comes down, that's the other half of the time. Well, I solved for time already at the top of the arc because that's where the vertical velocity is equal to 0. So the time, the total time, which I'll just mark this and I'll call this T2. T2 is just going to be double this value. So it's going to be 2 times V naught times the sine of the angle divided by G. So now I know how long it's going to be in the air. Make that a better 2. Now, what can we do with this? We should be able to calculate how far the projectile goes. And I'm going to call that the range, or D final. So I have an equation here for dx at some time t is the initial x velocity times how long it's in the air. Because remember, the projectile has an x velocity, and that x velocity doesn't change during its entire trip, during its entire time in the air. So I'm going to say that the range, I'm running out of board space here. Actually, why don't I just move this over here? I'm going to say that the range, which is, I'll call that D final, is going to be equal to, well, I have my dx right here, which is equal to v naught times the cosine of theta times t, but let's substitute t with this guy right down here. So I'm going to erase the t, and I'll just put all of that in parentheses, and I'm going to substitute this. So I'm going to say 2 times v naught times the sine of theta divided by g. So I multiply these together, and I can actually put this line all the way across like that. So notice that v naught appears twice. So I have v naught squared. I have 2 v naught squared, and I also have cosine of theta and sine of theta. Now, those of you who've taken pre-cal or trig may remember that there are things called trigonometric identities. And there's one, I don't remember them all. I don't remember very many of them. But there's one that's called the double angle theorem. It's one of the double angle equations, which is 2 times the sine of theta times the cosine of theta is equal to the sine of quantity 2 theta. Now, do I have a 2, a sine, and a cosine? I sure do. Here's a cosine, here's a 2, and here's a sine, and I have 2 v naughts. So I can combine these two terms, and I end up with my range, otherwise known as d final, is equal to v naught squared times the sine of 2 times the angle, all divided by g. And again, remember we moved g to the other side of the equation, so it's minus a minus positive. So all of this ends up being positive, and we end up with a range. Now, with this information, we can also solve for the angle that we need to get a range. We could rearrange this equation if we wanted to, and we could say that if I wanted the range, I could say the sine of 2 times theta is going to be equal to the range I want times g divided by v naught squared if I know my initial velocity. So if I take the inverse sine of this quantity, I'll get twice the angle. So I divide by 2, and that's the angle that I need. That's the angle that I need. Now, there are some other things that we also need to consider about this trajectory. This trajectory is a mirror image on the left side and the right side. So going up and going down, at any point on the left side, we can find the mirror image point on the right side. It will have the same velocity down as it has up, the same magnitude of velocity. Obviously, the direction is different. One is up and one is down, but the magnitude of the velocity at any point is the same. The same is true of the angle of impact. This is a vector, right? We have Vx, which has an x and a y component. When it hits over here, the x and y components are the same magnitude. This angle here, if it's 30 degrees from the horizontal here, then it will be 30 degrees from the horizontal, but in the other direction on the other side of the trajectory. So there are lots of things we can do with that. And now this is, of course, only true, and these range calculations are only true when we're looking at firing from one level to the same level. If we were trying to calculate what would happen after this went off of a cliff and hit down here somewhere, then we would need to ignore this T2. It would no longer be valid, okay, because it's no longer twice the time. We would have to plug the X, the new target, in to our dx, and we would have to solve for time a different way. Often it ends up being a quadratic equation because we have time and time squared in there that we have to get rid of. So that makes it difficult to solve, but we can still do it. We can still do it. So I hope this helps. I'll also post a couple of example problems after school so that if you struggle with this and you take it home for homework on the quiz, you can do the exam, or you can look at the example problems, and that may help you with the quiz.